Gee, sorry about that. I've been talking into a mute microphone. Good morning and welcome. My name is Darrell Rittenberg. Thank you for joining us this morning. Today we're going to be talking about faster exploration and analysis of parametric CFD results with Tecplot Chorus 2015. The presentation is really in two sessions this morning. We'll start with a setup of the problem. So we talk about the NASA flyer we chose. We'll talk about the way we set up the problem using GoCart from Desktop Aeronautics. Again, big thanks to them for letting us have access to the tool. We'll look at the design space that we evaluated and talk about the tutorial goals. For the tutorial, all the data I use today will be made available to people who attend or watch the recording. So if you want to go through and do the same work I'm showing here this morning, you'll have that capability. The tutorial will be in three basic parts. The first part will be evaluating a single solution. We'll talk about ways to look at things like convergence. We'll move into an alpha sweep where we'll evaluate a set of solutions, an alpha sweep, and we'll look for, well, we're effectively looking for alpha max, or at least understand if we've reached alpha max based on our alpha sweep. Then we'll move into design space exploration. Both the alpha sweep and the design space exploration will be done in Chorus. And finally, we'll talk about building reports. So that's the goal for this morning. And again, if you have questions, if you're new to the GoToWebinar platform, on your sidebar, you'll notice there is a little call out that says questions. If you have a question, don't hesitate. Just go ahead and type your question in there, and I'll try to answer it in context. A couple of quick thanks. Special thanks to one of our newest employees, Devin Simpson, who helped with both the running and initial workup of the data I'm showing you here today. Devin will be sitting in and answering questions along the way, if any should come up, primarily through the questions dialogue. Also want a big thanks to the folks at Desktop Aeronautics for, again, giving us access to GoCart to allow us to run these alpha sweeps. So the problem setup itself is simple. We were ideally looking to understand if we vary the vertical tail size and angle, and we'll kind of walk through those two details in a moment, and evaluate that effect on overall performance by looking at alpha sweeps. And we swept from minus 10 degrees to 25 degrees. We did beta sweeps from minus 2 to 15, and Mach from 0.3 to 1.3. The vertical tail angle we varied from 0 degrees to 15 degrees, and the vertical tail size varied from small, which is 250 square feet, to large, which is 750 square feet, and we'll walk through those as well. If you're interested, these references will be made available. You can get more information about the specific model, as well as, if you're interested, you can go get the VSP model directly from OpenVSP, and you could actually download it and run this case if you were so inclined. So a couple of quick notes on the rear wing geometry. So as I said, the two things that we varied were the angle, and so the angle we're looking at here is the angle relative to the body, and that we swept from effectively 0 to 15 degrees. We also did alpha sweeps. I didn't show what an alpha sweep is, but I suspect most of the people online today are familiar with looking at a sweep through alpha and beta. And the other thing we looked at is overall wing size. So you can see we have the large wing, medium wing, and small wing. And we'll look at the overall output variables in terms of stability for the different configurations as part of the tutorial. Again, big thanks to GoCart. We used the NASA N2A wing body without the engines. We used in an N+2 and N+3 studies, imported directly using the STL file. We ran nominally 200 iterations with a reference area and length of 1 and 70,000 volume cells. The extracts that we pull out of the solutions are actually a little smaller than that. That was intended to make it easier for people who ultimately are going to download and look at this data to go ahead and do that regardless of the type of machine you have. So these are very small solutions, so they're very performant. They could have been much larger, but the overall solution with the 400 cases we ran is nominally 36 gigabytes, so it is quite a bit of data. Okay. So the goals of the tutorial are really to walk through the use of Tecplot 360 and Tecplot Chorus. Ideally, we want to learn new strategies for analysis. We have a lot of people who are new to 360EX, perhaps have been using Tecplot for a long time. There are some things that have changed. We'll go through some of those changes as part of this analysis, so you'll understand what you did in the past and how you do it in the new version, and where the things are different. Some are more convenient. Hopefully some perhaps are new behaviors I'll have to learn. In addition, we'll talk about the use of macros. I'll show you how macros can be used to automate analysis. We'll create a project using the alpha sweep, and we'll take a look at how one can export those results into a report. So for those who are unfamiliar, Tecplot 360 is the biggest upgrade we've done in about 15 years. We've rebuilt our technology from the ground up. We're using Tecplot SDK, which is our engine, and Qt, which is the GUI development. As you'll see, we have significantly improved our performance both on large and small data, and updated the interface on Mac and Linux as well as Windows. So in this first part, the data file that we'll be using is actually the Mach 0.8 alpha 0 beta 0 solution. The idea or the goal of this part of the tutorial will be to evaluate the residuals, look at the moments and forces, and create a multi-page report style view of the output, and we'll go through that in detail. So at this point, we're going to get out of PowerPoint for a moment, and let's go ahead and look at Tecplot 360EX. So let me see if I can do that in an easy way. We'll go ahead and get Tecplot 360 up and running. And we'll look at the, we're going to look at the files. Now, all these files are made available to you. They will be in a directory called Chorus Project NASA Wing Body _400. In that directory, we'll have tutorial part 1, tutorial part 2. Okay. And this example, we're going to do tutorial part 1. So this is the path for my computer. Of course, the path for your computer will be a little different. We're going to start by making a new layout. Really, two ways to do that. If you hit new layout, it brings you basically just where you were in Tecplot 360 2013. Not much difference there. I'll hold shift and zoom in on the paper a bit, or the work area. And from a loading perspective, we have made some updates, specifically that we've actually, in principle, we used to load layouts and read data files, etc. We now have one unified interface, so if you want to load a data file or a layout, it's all part of the same environment. So we'll start by looking at a data file. And again, these data files are in this directory. And you'll notice that there's a Mach 0.8, alpha 0, beta 0. And there are several data files here, combined, which is a PLT format. For those of you who are unfamiliar with Tecplot or less familiar, PLT files are typically binary. They tend to be both smaller and load significantly faster. On the other hand, DAT files tend to be ASCII files. These are, not that that's a problem, it's just that we convert ASCII files to binary files as part of the load process. A large ASCII file may take several seconds to convert, and therefore it will slow down performance. So in general, it's better to use PLT files if you can. We also have the components. This actually is the surface in a DAT format, which, as I mentioned, is ASCII. Cut planes, these are the cut planes we set up as part of the go-kart run. Then we have the convergence history and the moment and force history. So we're going to start by evaluating the model by just looking at the component data. Now, as I load this in, you'll notice that it did convert it, although, again, it's quite a small model. And we'll look at this in 3D. So here's our model. You can see that this is the nominal case. It's the medium-sized rear wing or tail section with 0-degree angle. So this is our base model. And we can very quickly, in Tecplot 360EX, a simple right-click brings up access to layers which typically one needed to access via the Zone Styles dialog. So initially, if we chose to just evaluate the mesh, we can turn on the mesh. As you can see, it's a relatively coarse mesh by design. We can also change very quickly what's shown on the mesh. So in principle, if I wanted to look at CP, I could change the mesh color to CP, and we could evaluate CP on the body, at least at the end on the mesh lines. To turn off the mesh, again, a right click can turn off the mesh. We can turn on the contour, so now we can look at a contour of CP. There are no vectors on the surface in this case, so we won't be looking at that. We can also control things like translucency, so in this particular case it's not relevant, but if you're looking at an internal flow, or perhaps if you're looking at a slice, you may actually want to turn on the translucency. Again, if you're looking at a multi-block solution, you want to look at the edge. You can turn on edges, borders and creases directly from this interface. Similarly, you can look at the shade and shade color, both turn it on and off, and vectors and vector color, just again in one main interface. This was done to make it a little easier to get to the plot of interest. Much of that same work could be done via the Zone Styles dialog. We have updated the Zone Styles dialog for those of you who are new to 360EX, whereas we used to click on the top of the header of the particular table. If you click on Zone Style here in Zone Show, for example, nothing happens. Now you have to click on the checkbox, it turns it off and on, or a right click will get to the menu that you're used to: activate, deactivate, select, use show selected only, and invert. So that's a little bit of a change, and again, depending on your familiarity with Tecplot, there may or may not be a problem. Other things that you should be aware of: we can view pages. Now, the pages concept is somewhat new, although in the background of Tecplot 360 we've had this for some time. The idea of pages is that I can call this the 3D plot view of a surface. So this is a page. Now, a page could have multiple frames. So if I wanted to, say, look at, in this case, multiple views of this, like, say, the principal views, I can use the 3D multi-frame. And in this case, what I'm going to do now is, you can see I have, I'll move this over just a bit. So we have in here, so we have the main body, at the view that I was looking at initially. And then we have the YZ, the XY, and XZ plane views of the model. So we'll leave this alone for right now. If I want to remove this, you can go back to this 3D multi-frame and remove it. Now we're back to just square one. Other things that are kind of interesting: if I select the frame itself, right-click, I can copy the frame. Now, two things. One, that copies it directly to the clipboard. If I went back into PowerPoint, for example, which is over here, or I guess I can move it over, and pressed paste, Control-V, you'll see that it will paste in the model. So it's on the clipboard. That used to be under Edit, Copy, Plot to Clipboard. There are some capabilities that aren't there right now, but for this example, it isn't critical. I'm going to add another page, and I'm going to double-click on the name of it, and we'll just call this 3D Slice View. And you see when I open up a new page, it has a frame. I'll just paste my existing frame. Remember, this was the frame up here. I'll go back. I do want to keep this as the multi-view, so we'll do that. And now let's go ahead, and I want to talk about a couple of things, and this is data extraction. And this first part of the tutorial is primarily just to familiarize those people who are not using 360EX today, maybe don't know some of these capabilities exist. So we'll start with some new enhancements to the slicing. We're going to look at a Y slice, and you can see that there's three types of slices we do now: the volume zones, You can select the surface of volumes, or you can just do the volume zones. Now we want a surface zone. We could move that to, say, about 10% of wingspan, or 85% of wingspan, depending on your point of view. And we can also add a start and end slice, and then move the start and end slice. So perhaps let's put the end slice there and the start slice over here. I'm going to turn off the primary slice. It's unnecessary. I can add intermediate slices, perhaps 3 of them. So now we have about 5 slices on the wing. Move this out of the way for a moment. In the past, if I wanted to slice a surface like this, I would have had to done this by a macro. If I wanted to extract, say, CP at these slices, I would have done a data extraction. Today, you still can go current slices. In this case, it's going to extract the surface slices. Or perhaps more conveniently, if you select one of the slices and right-click, if you right-click on the actual slice group, it tells you slice group 1, and you can do a hide or extract. So in this case, ultimately, you want to extract. So if I hit extract, it's going to extract all the slices. If I go to design styles now, you'll see that we have slices from y equal 101 nominally to about 60. So now that we have those slices available, we're going to come in, add another slice, and we'll call, or another page, and we'll call this CP plots. Okay. Now these are going to be non-normalized. We do have a macro available that will come with the data that will normalize CP so that they all start at x equals 0 since it's a swept wing. Not going to worry about that right now. So let's go into the line mode, and a couple of things again that we've changed. If you move into XY line mode, it doesn't automatically start creating lines. It basically prompts you to say, okay, what do you want to look at? I want to look at y-axis variables for all linear zones. So the x will be x, and y I'm going to choose CP. And you can see here are those CP cuts along the wing. Now, a couple of things that you can do. You can right-click directly on a curve, change the curve type if you're doing a curve fit, or you can change the line color, say to black. We're making some enhancements to this. Pretty soon you'll be able to change most of the attributes that you would do under zone style. But in this case, I'll just select all of the zones that we're interested in, and we'll go into the line properties and change this to 0.4 to make them a little thicker. Okay. Other things, if you right-click on or double-click on the axes, it will bring up the axis edit dialog, and we'll go to range on Y, and we'll reverse axis direction. Okay, so now we have our CP cuts. You can also, under plot, do a line legend, and if we show that here, if we right-click on this box, I can change this to a filled box or no box, which is what I want for this case. If you hit minus and plus, you can also play around with font, but in this case, I'll make it a little smaller. There you go. Okay, so we have that first fundamental view. We have our view of the slices, and we have the CP plots. The last thing we're going to do is we're going to load in the residuals. So let's call this history. And let's go ahead and load that data. So we'll go here, and we're going to grab the history and open that up. Now the history data comes in as V1 and V2, which basically is CPU time and number of iterations. Not particularly important. What we are interested in would be number of iterations instead of V3. We'll change this to say, let's see here, definition. There we go. So we'll say V3. Okay. And then we'll hit Control F. So what we're looking at now is the residual history as a function of the number of iterations. You can change the text. This file itself actually doesn't have any header information. It's probably worth showing just for kicks. Let me just show you what it looks like. I don't know if people use Notepad++. I'm rather partial to it. So this just gives you information about, you can see it basically ignores all of this because the dollar sign here, or the number sign, makes it a comment. And then you can see that cycles, CPU time, max residual, global residuals. All right, so let's go ahead then and close this out. Here's our history plot. Let's make one more, which will be our moment. And the moments will do the same thing. We're going to load those in under moments, open that up. And again, we'll change this to look at the moments. So we'll look at V5, these two, and turn off this one. And we'll hit Control F. So that's actually the moments. And there should be a second line. You can't see this. There's X, Y, and Z moment. So ideally at this point, this may be kind of a workup of a single file. What we can do with this is actually save this as a layout. So the layout itself, we're going to put it in the same directory. Under the course examples, under tutorial number 1, we'll call this the all data and plots layout, and we'll save that. Okay. If it's, I think we did the extraction, it's trying to save it, that's fine. We'll just put a binary file in, call it the extracts. Okay, so this is kind of what we want to do for a single case. It's a lot of information to look at. I want to go back to the to PowerPoint deck now, and we're going to talk about tutorial number 2. Again, if you do have any questions, if I'm going too fast, let me know. I do this for a living, so I tend to go way faster than most people would. So if you are running behind a little bit, say, just go ahead and raise your hand. Okay, so let's go back to PowerPoint for a moment here. And let's see here. Okay, great, sorry. Okay, let's see, is it coming up? Yes, it is, okay. All right, now we're going to move into Tecplot Chorus. Tecplot Chorus is a tool designed to help people who are looking at multiple solutions, and multiple could be one. If you have, say, within a single file, you may have multiple configurations that you're evaluating. It could be a simple alpha sweep, as we'll go through in our first example, or it could be thousands of solutions that maybe come out of a low-dimensional code that you're evaluating a dimension or high-dimensional design space. Really depends. Chorus is great because it reduces the necessity for both scripting and allows you to evaluate changes across the system very quickly. It leverages 360EX, so you do get the capabilities of what I just showed you a second ago. So, and it's really simulation analytics, which is bringing together visualization, data management, and statistics across a set of CFD solutions, but it's really agnostic, so in principle it could be any kind of data. So, although CFD data works great with it, we've actually done cases with data from PIV. We've done geophysical data. We've had people look at water flow measured via river instrumentation, and we have had people look at electromagnetic solutions in this environment. So it's flexible, really depends. The key being that you have a set of solutions. So what we're going to do in the second tutorial is to evaluate AlphaMax for a single mock run. We'll show you how to create a project. We'll evaluate the moments and forces. We'll analyze the data in Chorus, and ultimately we'll use that as a transition into a much larger, higher dimensional space. So with that, let's get out of 360 again, and let's go ahead and launch Chorus. Now, Chorus is built with similar technology. It uses the Qt UI. It uses aspects of different drawing libraries and is connected to Tecplot 360. The main concept is that we have the idea of projects and sessions, where a project is really kind of the underlying data that defines a collection of cases, and a session is a view of those data, whether it be plots, images, as we'll go through here in a second. Okay, we're going to start by creating a project, and there are two ways to generate a project. First, we're going to show you that you can create a project using a CSV file. So let's go ahead and do that now. Okay, so a CSV file loader is quite simple. I have it here under tutorial number 2. This is a simple CSV file which will actually open in Excel so you can see kind of what we're looking at. I'll wait for that to update. Okay, so as you see, we have V-tail, which in this case is the angle of the tail. The size, this is the relative size. The size of the rear tail we're looking at is 750 square feet. It's the large tail section. The Mach that this was run at, in this case it is a constant Mach of 0.5. We're doing an alpha sweep from -1, or -5, pardon me, to 25. And beta staying at 0. The size Boolean, don't worry about, that's just a number to represent that it's a large case, and the number of iterations. The other variables here are all output variables, and that's the force on the end, the Y force, the X force, the Z force, the moments, and then CD, CL, CY, CM, and CN. Okay, so that's what's contained in the CSV file, and we're going to go ahead and open this up. And you'll see that it creates a quick table view. I'll let that update. And also you'll see that there's some null values. And this is an artifact of there was a number of carriage returns in the CSV file that we don't really need. So you can see that Chorus didn't know if they were real, so it brought them in as cases. Not a big deal. You can actually just delete them in a single click. So, okay. So we have now data which is basically the output variables. So we have the input and output variables. We use nomenclature of variable nature, which we have independent and dependent variables. So for example, the tail angle is an independent variable, Mach, alpha, and beta independent variables, size, number of iterations. The forces, however, are dependent. And this is, I'm just updating these for plotting capabilities you'll see here in a second. So I'm just updating these to dependent. We're in the midst of making this a little easier so that you can designate the variable nature in the CSV files so that one doesn't necessarily have to update them. And although for what I'm going to show I didn't need to do this, since I'm here I'm going to go ahead and do that. Okay. So let's quickly take a look at the data. So we'll evaluate then as a function of alpha. Let's look at CL. So we'll do x-axis is alpha, and we'll look at the CL curve. So this is the lift curve for the set of data. Each one of these points you can see are actually cases, but those cases don't have data. We didn't include data in our initial project setup. So I'm going to go through the process of bringing in the actual data file so we can do some additional analysis. And let's go ahead and do that now. So the project itself, we're going to append data. In this case, the appended data are the actual data files. And we'll use a file crawl. Now, what we're going to be doing is leveraging the fact that we used a systematic naming convention that is automatically put together via GoCart, so they've actually built their output structure so that it's quite easy to pull in data. Okay, and let's start with the first directory, which is the V-tail size. So if I type in V-tail with an underscore, you'll see that it will identify the fact that the angle is 0. 2 more tabs, and if I type in size underscore, you'll see nothing happens because I am looking for a number, but if I tell it text, you can see that in fact it's L. Now the actual directories under that directory, so these are the subdirectories, have Mach in them, and Mach is a number, alpha is a number, and beta is a number. And that's all we need. And basically what this will do is it will actually connect to our table. This is the angle, size, Mach, alpha, beta, and I guess the size of Boolean isn't necessarily part of the directory structure. Okay, so now what we're looking at is files, and we're going to start with the surface data from directly output from GoCart. So to get that, I can just type in i.dat, and you'll see it says component, but this is really the ASCII surface data. Okay, we want to bring in the combined data, which is in PLT, but there's only one PLT file, so I can just bring this in. This is the binary surface and cut planes. Okay, and we probably want to look at the forces and moments, so let's go ahead and we'll bring in the force data. So we'll just type this in here. And that should get the, did I misspell that? Yeah, I got you. Let's see, forces data. And this is forces, so, and we'll do the same for the moment. Moments.dat. Okay, and that's probably fine. These are binary, or these are ASCII files. We could bring in the cut planes. Probably don't need to, but if you wanted to, you could connect the cut planes. You could also connect images if there were any. In this case, there are none. So we'll hit next, and you can see that it's grayed out here because it identified these as variables that already exist. When I hit finish, it's going to say, hey, do you want to add these as new cases or modify existing cases, which we'll modify. All right. So now if I were to go look at any one of these cases and go to view data, you'll see that the ASCII surface, the binary surface, and cut planes, forces and moments are all there. Let's just grab the cut planes, and we're going to use a surface or a style file, and I'll show you how we got there here in a second. But now when we do this, it will actually fire up 360 and generate a plot. This is actually case 8, and I can see what the independent variables are for that case. Okay, and I'm going to change the color map here, the coloring for pressure, which I think is modern. Let's go ahead and change that to like a large rainbow. And for this example, let's actually look at the bottom surface. Since we're doing an alpha sweep, maybe this would be a good way to understand how things are changing. And let's make this a filled box, and let's move it up a little bit. Okay, so this is a style that we want to apply across all of our cases. So we're going to save this as a template, and we'll call this bottom pressure. So, all right, so we have the bottom pressure, and we're going to go in now to our project. We will select all the cases, a simple right click, and we are going to create images. So basically we're creating a set of plots based on this data. Now if you were doing this on an HPC facility, you would likely probably pre-process your data and have images or extractions available to you, which you would have brought in the project. In this case we don't have them, so we're going to go ahead and just look at bottom surface here. All right, and I'll hit OK. You can see down in the corner it says Manage Jobs. What it's saying is, okay, it's creating images on the bottom surface tag, and it's in progress. So one thing we're going to be adding in is a progress bar. Hopefully you can see this update, but you can see it's taking about a second or so per case, so it shouldn't take too long. There's only 16 cases here. In the meantime, well, they're done. So actually, we'll just go ahead and deposit those. Now, if I grab, say, the nominal case and say the highest alpha case, I can view those images very quickly. Oops, I must grab the wrong style, but that's okay. But you can see what the variance is between those two very quickly. So there's the two images. Let's go ahead and grab all these again, and we'll create another set of images. And let's actually use the right style, and we'll call that minus bottom pressure, doesn't really matter. Let it go through and do it again. All right, let's go ahead now. We'll look at this data here. We're going to, let's look at the -1 and 25 case. Now we're going to view the actual data. We'll bring that up. So here are those two cases in Tecplot 360. So you can see this is the alpha -1, alpha minus, or at 25. If you want to look at the variance between these two cases, one can actually show a difference. So now we're looking at the delta pressure below, okay, between the nominal case and the regular case. And you can see, let's see here. This is the difference, pardon me. Okay, so now we're looking at the delta. This is a quantitative delta between the two. Going back into Chorus, let's go ahead and put in this new image we just created, and then we'll look at those images again. Now you can see it's a bottom contour, and we can do a qualitative delta using a simple image difference, which shows us the delta between the contours. Since the contour levels are the same, it's giving us similar information. It's not as quantitative, perhaps, as this view, but you can see that it is qualitatively similar. Okay. Okay. So that's looking at just the one set of data. What I might want to do then is look at maybe one additional view where we're going to open up the moments data. Now remember, this is the same set of data we looked at a moment ago. We're not going to worry about the CP extraction, but we will go ahead and open that up. And so now this is that V1, V2. We'll change quickly that we really only want to look at these two and not that one. And I hit Control F. Now you can see that the ranges are a little bit off. So in order to put them on the same case, because I think we're looking at some of the pressure in yaw, and since the beta was 0, you're not going to see that. It's going to be relatively small. So one thing that you can do is actually go to Y2, and then if we hit a Control F, we can actually see both of them. Since these images are going to be relatively small when we look at them in the context of the entire project, we'll make the line thickness a little larger so that it's more pronounced. And double click on this, we'll use text. So for the Y1 axis, we'll call this X moment, I believe. And for Y2, we'll call this Y moment. It's not important, really, it's more the exercise. And for the x-axis, we're going to use number of iterations. All right. Okay. So this is the style that we want now. We're going to go ahead and save this template. We'll call this moment. And we'll go back into our project. We'll select all the data. We're going to create another set of plots using the moments data and our new style template. We'll hit okie dokie, and again, that's going to go through and run one additional set here. So, and that should only take a couple seconds, and while it's doing that, we already showed you can look at the plot itself. If you want to look at, there seems to be anomalous behavior in these two cases. We can actually view the images very quickly, and we can look at both images together versus the cases and say, okay, is that dip real? Is there something here that would give us confidence that the dip in the lift curve is in fact real? We'll go ahead and deposit these in which case you can actually look at all three. So you can see that we're a little off scale on our moments, not a big deal. Okay, so ultimately, if you're working with just one set, you can see how you can go through and very quickly analyze these data. We can also look at a matrix view where effectively we'll look at alpha as a function of the, let's see here, tag, which basically are the images. Let's let's just make sure we're looking at the right thing here, and we'll zoom out, and you can see the images that we have as a function of, oh, okay, the alpha and force, that's what's going on. Tag, not there. Page bind, none. All right, so there and you can see we have all the different alphas, and we can very quickly walk through or evaluate how it's changing for the entire system, including looking at the moments. And we probably want to go in and update this style. You can see that when I do select that case, it very quickly shows me where I'm at, and so I can do a quick view data. And if we go back over here, you can see it's off scale. We can hit Control F. Now this is a better axis, better axes for the moments that we're looking at, and so I could just update that style template. And you can see that in effect, if I go back into my project, and we can go ahead and create another set of images. We'll go from there. Okay. So at this point, we've kind of walked through how to work with a single image or a single case. We've worked with 16 cases, but now we actually want to evaluate a larger design space. And so in this case, we're going to go back to the original intent, which was to look at 3 different wing configurations at multiple angles and at multiple Mach and alphas. So it's a little higher dimensional case. It's about a 4-dimensional case here. And we'll just go over here and unselect you and select you, and that should look a little better. Okay. All right. All right. Oh, we're doing case ID. All right. We'll close that. And now I talked about this a little bit. If I like this particular view, I can go ahead and take that one off. I can go ahead and update this very easily. What I can do basically is save a session, which I'll do. And this session will be in the folder, so if you want to play around with it, you certainly can go ahead and do that. So I'll hit save. It's going to be a session, which is CHSES file, and we'll go ahead and make sure it's in the right directory, which is here under tutorial part 2, and we'll call this T2. And we'll go ahead and save it. Okay, so let's take a look at the full set of data now, and we're not going to go through some of the mechanics because we've already kind of done that. So let's see, for each, this is the full set of data, and if I open up the full set real quick in Excel, you can get a sense of what we're looking at. So we're looking at about 422 cases. We're looking at alpha sweeps from -1 to 25. We're looking at Mach sweeps at 0.5, 0.8, and then we've done a few Mach sweeps in general under a nominal case. We're also doing beta sweeps from 0. If we go up here, you can see that we went as high as 15. So we have lots of information, the highly dimensional space. Let's go ahead and take a look at that in Chorus. So I've already created a project which I've basically followed the same strategy that we did before, only I've done it for a larger set of cases. And we are going to go ahead and open that now. Okay. So we'll just start with the basics. Here are the cases. You can see that there are 415. We actually didn't bring in the last 7 or so cases, or 8 cases in this case. And over on the filter side, which we haven't really talked about filters, but we'll talk about them here in a second, we have the size. So this is the large wing, the medium wing, and the small wing. The Machs, so these are the individual Mach that we ran each case at. The alpha sweep, so went from -10 to -25. Beta from -2 to 15. The size, this is just a number. I'll show you why that's important in a second. And then we have forces and moments, as well as CL, CD, CY, CM, etc. Okay. And let's start by just looking at the design space. So we're going to look at Mach versus, in this case, the angle of the tail. And for the y-axis, I'm going to move this over here temporarily. so you can see both. For the y-axis, or the z-axis in this case, I'm going to use the size Boolean, which is basically the size of the rear wing. So, and there's only 3 sizes, right? There's 0, 1, and, or I'm sorry, 1, 2, and 3 that represent small, medium, and large. You can see that we ran mock sweeps on some of them, but not all of them, and that we ran at 0, and I think this is 10 degrees for the angle of the wing. We ran several of those. And under the medium, we ran one with a 15-degree sweep angle, or rear wing angle. So this is part of our design space. We could also look at mock, alpha, and beta to just look at our initial condition space. And you can see we ran several cases at Mach 0.8, several at Mach 0.5, and then a couple of Mach sweeps, and alphas ranging from -10 to 25, as well as you can see we ran some betas as well. So the idea is this is our dimensional space. We want to evaluate the performance of the vehicle, and we'll do that in the next about 10 minutes just by using our filters. So let's start by looking at something a little more interesting. Perhaps let's look at the alpha sweeps. So on the z-axis, let's look at lift. So now we're looking at the lift curves. You can see that there's a couple here that we ran at a CL. So on the area of Mach, rather than Mach, let's go ahead and look at the different size of the wing. So because we want to understand about effectively how this performs. So you can see we ran at small, medium, and large, and you're looking at the individual lift curves, and you can kind of get a sense of how this is behaving. Now, I can evaluate individual Machs by going to a single value filter now, and I can walk through and find the different alpha sweeps. And so this is at Mach 0.5. And I can also apply a surrogate model to this. So I'll set up a surrogate model by adding in our independent variables, and we'll show that model here. So this is a model of the lift surface. You can also change this to the to drag as well. So this is the drag, or we could even look at CDCL as a line plot, which we'll do here in a second. So let's put this back at lift. Okay. And quick Control R if you want to reset the plot. Now, if we want to look at, say, a series of images for a set of cases, and let me go ahead and select a few of these. So I'll rotate this around just a bit. And let's select this set of cases and go ahead and view the images. So now we're looking at a particular set of cases. So these are the cases of interest. We have quite a few views of the data. You can see we've done an extraction of CP. This is non-normalized for a swept wing. We can also label these things. So if we want to know the independent variable space we're evaluating, we can do that here. So now we know that this is beta 0, Mach, or alpha -2. So you can see these are all basically alpha -2. And at 0. And you can see what the net impact is just by scrolling through the cases that we've selected. And that gives us a very quick way to kind of see how things are changing, or what the impact of the independent variables are on the overall performance of the system. All of these data that I show you here were created in the same way with a right click, and we did a view data effectively where we looked at, say, the combined data with, let's say, the combined 3D view or the CP extract and no style. And if I do this, basically it's going to do the extraction of CP, and I believe if I go into align mode, you can see this a little better by looking at X versus CP. And there you go. So there's the CP curves. So it does an extraction. So hopefully at this point, I'm going to pop back into PowerPoint for a moment. We talked about working with a single set of data. We've talked about working now with the entire set of data using filters and data views, applying surrogate models, and evaluating matrix views, which are those views that show multiple extracts of the output variables as a function of input variables in both image and plot form. So with that gets us to the end of the tutorial. All the data and the recording will be made available hopefully by this afternoon, and so you can walk through these data at your leisure and follow along. So I'll go ahead and open it up for questions. We have about 5 minutes for questions, so if you have any questions, go ahead and type them into the questions dialog. And I'll go ahead and open it up at this point. Okay. First question. Okay, well, so how did you write the macro for the extraction? I'll include the macros, so for those people who are interested in seeing how that macro is written, you can actually go ahead and look at that as well. I'll open up to other questions. All right. Well, it doesn't look like we have any additional questions. Thank you again for following along today. If you're interested in helping us design Tecplot to be the best tool possible, okay. Oh, sorry. Yeah, it says please tell me when this is being posted. Yes, I will get this posted and send an email to everyone. But if you're interested in learning about what we're doing, go ahead and become part of the beta community. We have about 350 active beta users in the community. Hop over to tecplot.com/be a beta tester and go ahead and fill out the quick survey, and we'd love to have you on board. And yes, the tutorial will be available both in video form and the data, hopefully by this afternoon. Again, thank you very much, and see you at the next tutorial. Thanks again.